push the Cayenne EV to near supercar charging speeds. But the real trick isn't volts or kilowatts, it's temperature control. What this video covers and why you should care. We'll strip this down to the guts, how Porsche's battery thermal strategy, BMS logic, and high voltage architecture work together to squeeze high charging power out of a heavy SUV without frying the pack. I'll show you the exact temperature windows that matter, how charging power changes across state of charge, the efficiency trade-offs, and what those numbers mean for real-world charging time and a battery life. If you fast charge, tow, or just hate waiting, this one's for you. The basics first. Why temperature is king? Batteries don't like extremes. Too cold and ions crawl, too hot and chemical reactions run away. For high-speed DC charging, cells must be in a narrow sweet spot, where they can accept lots of current without plating lithium or overheat. Porsche's designed the Cayenne to heat that sweet spot faster and keep it longer. That's why you can see huge charging numbers on the spec sheet that actually translate to real charging time in every use. Inside the Cayenne's battery system, the headline specs. Porsche's new Cayenne Electric uses a large high-voltage battery of about 113 kWh with double-sided cooling and an 800-volt electrical architecture. That layout lets the car charge at up to 390 to 400 kW on the right condition. The pack's double-sided cooling pulls the heat away from cells from both faces, which flattens temperature gradients and keeps the whole module in that charging-friendly window longer. Those choices are deliberate. High energy, aggressive cooling, and higher voltage creates the pathway for very fast, efficient DC charging. Here's the critical detail most headlines skip. Porsche says the Cayenne reaches its optimal fast charging curve from a battery temperature of just 15 degrees centigrade. That means you don't need a tropical day for top performance, but you do need the battery around that temperature before you slam in hundreds of kilowatts. If the battery is colder, the car limits power to prevent lithium plating. If the battery is already hot from heavy use, the BMS already throttles to protect the cells. Get the temperature right and the Cayenne can sustain very high power over a wide state of charge. Miss it and the charger backs off fast. Let's make this visual in words. When you arrive at the DC charger with a near cold pack, the BMS does the math: temperature, cell impedance, and state of charge. Power might start conservative, then ramp up as the pack warms and chemistry permits. According to Porsche's data and independent testing, the Cayenne can draw more than 300 kW even from very low state of charge, and maintain more than 350 kW up to roughly the mid 50% state of charge, at which point cell temperatures climb into the 50 to 55% range and the pack can no longer safely take the same current. That's the practical ceiling where efficiency and safety force the car to slow the charge rate. Why double-sided cooling matters here? The engineering behind even temperatures is in this. Heat generation in cells is not uniform. One phase heats faster depending on local current density and cell layout. Double-sided cooling gives heat a path out on both sides, drastically reducing peak temperatures and local hotspots. That matters because hotspots are the earliest trigger for BMS throttles and long-term aging. With even cooling, the entire string shares the thermal load. The BMS can use more aggressive charge curves and average cell stress drops, which improves both short-term charging speed and long-term health. This is one reason Porsche can sustain high DC power over a wide state of charge range in the Cayenne than many rivals. The battery management system is the traffic cop between charger and chemistry. It constantly estimates cell temperature, internal resistance, and plating risk. When the BMS sees a risk of plating or temperature runaway, it reduces current, switches thermal loops, or requests preconditioning. Porsche's strategy pairs an advanced BMS with predictive control. If navigation says you're heading to a fast charger, the car can warm the pack en route so it arrives ready to accept high current. That predictive preconditioning is a small UX win with a big impact on real charging time. Turning up charging power eats into efficiency. Higher currents produce resistance heating, which wastes energy and can shorten range if you're charging frequently. Every kilowatt pushed into the pack produces some heat. The cooling system uses energy to remove it. Engineers balances this by letting the car accept very high power for a short window, where the time saved outweighs the sight of energy loss. Then tapering to prioritize efficiency and cell longevity. So a 10 to 80% fast charge number looks great on the brochure, but the real cost is the heat and the percent of energy lost in the thermal management. Good BMS strategies minimizes waste while still delivering useful speed. Picture this, you pull up at a 400 kilowatt station with the Cayenne at 20% and a battery around 20 to 25 degrees Celsius because you drove from a warm garage. The BMS allows an aggressive current burst, you see power surge into 300 to 380 kilowatt range, and state of charge climbs fast. As the pack moves past 50 to 55%, internal temperature approaches the thermal limit, and the car begins to taper power to protect the cells. The result? The bulk charge is blistering fast, but the final 30% takes longer and you lose some efficiency to cooling work. If the battery had been colder on arrival, the car would have warmed the pack or limited current until the chemistry was safe. Those exact thresholds and timings are why Porsche's engineering focuses on maintaining the right pack temperature before and during charge. Road conditions also vary. Wintry mornings, repeated spirit driving, towing, or track runs. Each scenario compounds thermal stress differently. Heavy power output followed by fast charging can bring cells close to those safety bands. Cold starts make the opposite problem. Low ion mobility and plating risk. Porsche's testing program froze all of these at the Cayenne in virtual and real world cycles. So BMS logic, coolant flow rates, and heating strategies are hammered into reliable routines. The goal is consistent user experience, fast when safe, conservative when necessary. Charging at hundreds of kilowatts is thrilling, but the pack must survive thousands of cycles. Repeated high power use raises average cell temperatures and mechanical stress. The BMS aims to optimize for life by limiting the time spent at extreme temperatures and favoring charging profiles. Porsche's blend of cell chemistry choice, cooling architecture, and smart BMS is tuned to heat a balance, allow dramatic charging speed while keeping degradation within acceptable commercial limits. That's the engineering tightrope. Shave seconds off charge time without shaving years of battery life. What this means for you. If you own or will own a Cayenne EV, precondition when possible, use en route charger pre-warming to heat the 50 degrees Celsius sweet spot. This saves minutes at the charger and reduces stress on the pack. Expect blistering speed in the early to mid state of charge band, then taper as the pack gets warm. Don't judge charging performance from one cold start. Ambient temperature at arrival changes the story. Frequent ultra-fast chargers are great for speed, not for maximizing battery lifetime. Spread them out if you can. So why Porsche's approach matter here? Porsche didn't just slap bigger cells in a Cayenne and call it a day. They engineered a system-level solution, bigger energy, better cooling surfaces, and 800-volt backbone for lower current at a given power, and a BMS that predicts and protects. Together, these elements let the Cayenne be both a long-range SUV and a vehicle that can recharge like a sport car. In the real world, not just on the spreadsheet. That's the engineering victory. Performance with predictable behavior under stress. Manufacturers publish ideal numbers, but independent long-term data matters here. Questions remain about how sustained high-power use affects real-world degradation over 5 to 10 years, how well the thermal systems perform for far beyond lab cycles, and how software updates might change charge behavior. Also in the extreme climates, the preconditioning energy cost becomes relevant. Warming a huge pack from freezing takes a real energy, which affects range and charging math. Watch for independent long-term testing and real owners' data to validate Porsche's claims over time. Temperature control is the unsung hero behind Porsche's charging numbers. Double-sided cooling, a high-capacity battery, 800-volt architecture, and an intelligent BMS let the Cayenne accept massive power while protecting cell health. But power has trade-offs. Efficiency, thermal load, and lifetime all factor into whether those fast charge moments are cost-effective in the long run. Want a deep dive in the battery management system, the modules, packs, cell level, and how it is being designed? You can click on the links in the description. Thank you.